Okay, so I'm gonna back up a step so that we kind of cement in some of what we learned about the confidence interval. So there's a document on Blackboard. Here's the lab session 7. This document called exercise 1, lab exercise 1. I'm gonna open that up. It's a Word document. And there's 3 problems on there. And I'm gonna start with the second problem because it's a little bit more familiar to us than the other 2 are, I think. Okay, and I'm gonna read it, and it's gonna be a basic look at the confidence interval again. Okay, so we go to randomly select, unfortunately it's St. Patrick's Day example. It could have been a Halloween example like the homework, but what are you going to do? Randomly select 40 New York City pubs. I didn't even think about this, and find that the inventory that on the average they inventory 42 types of beer. You calculate the standard deviations for those pubs from your study data and find that it's 6.3 beers. So you went to 40 pubs, the sample size is 40, and found that on the average they carried in one form or another, bottles on tap or whatever, 42 different kinds of beer. And that standard deviation for the number of types of beer that each bar carries is 6.3. So what do we know here? We know X bar, right? We know the mean, which is 42. We know the sample size, which is 40. Do we know the population standard deviation for all bars in New York City? No, we don't. So the only thing we can do here is estimate the population standard deviation, sigma, from the standard deviation of our sample. Turns out it's 6.3. Okay, we could have a lively debate right now over what we're going to define as a large sample. Like from one perspective, you could say that, gee, if I want to assume that I really know what sigma is for the population, I want a really big sample, like 200 or 300. If on the other hand, I want to say, well, I really don't have a good handle on it, we might say less than 30. So for our purposes today, I'm going to say anything bigger than 30. A lot of textbooks tend to do this. Anything big enough than 30 is big enough for me to say that I have a pretty good rough idea what sigma is, and I'll use that as sigma. I'm just doing this on purpose so I can contrast that to a really small sample. So let's take a look at what we know here. We know, and let me just open this up, give myself somewhere to write. Okay, I'll ignore that number. Okay, so we know X bar was, what was it, 46, 42? 2, and the sample size is 40. And we're going to say that we know sigma is equal to 6.3, right? We're going to assume that that's a big enough sample size for us to estimate what sigma is. So if I wanted to calculate a 95% confidence interval for this, I would say to myself, well, I'm going to start, the middle of my confidence interval is going to be my point estimate or my mean. So it's going to be X bar plus or minus, and my margin of error, what I'm going to subtract and add to X bar in order to get my 95% confidence interval is going to be my Z-score, right, for a 95% confidence interval, times my standard error. Okay, my standard error is going to be calculated based on the standard deviation of the population over the square root of the sample size, or 6.3 divided by the square root of 40. Okay, so what am I going to use for Z? If I decided that my sample size was large, right, big sample size, what can I use for Z? Yeah, 1.96, right? Okay, if it's small, then I have to deal with this extra uncertainty, and I can use the t distribution instead. So I'm going to say X bar is 42 plus or minus 1.96 times my standard error, which is 6.3 divided by square root of 40. So let's calculate that. I'm going to clear this out. 6.3. Oh, hang on a second here. Let me do the square root of 40 first. 40 square root. I'm going to put that into memory. And I'll clear that. So 40 divided by the square root of, 6.3 divided by, let me try this again. 6.3 divided by the square root of 40. So that's going to be equal to roughly 1, right? I got a little lucky this time. Now, I'm going to take that standard error and multiply it by 1.96, so I'm going to do that right now. Whoops. Got to do it again. Let's see. 6.3 divided by memory times 1.96 is equal to 1.94. Okay, so this whole thing, I'm not going to worry. My whole margin of error is, see what it was again, 1.94, right? Yep, 1.94 plus or minus 1.94. So our confidence interval is going to be 40.06, right? And 43.94. Thank you very much. Good. You save a lot of time if you help me out with these things so I don't make a mistake. Okay, so what does that tell us? What does that mean exactly, that confidence interval? What does that tell us about this world where we have Irish pubs that have a lot of different kinds of beer? What does it tell us about that world? It tells us that the true mean is likely between these two numbers, right? What level of certainty do we believe we have here in terms? Yeah, now we're 95% sure the true mean for all the pubs in New York City, all the Irish pubs in New York City, is between these two numbers. We don't know it for sure, but now at least we have a range and a level of confidence. If I were going to calculate this where I wanted to be 99% sure, would the range be wider or narrower? Wider, because I want higher certainty. And what would make it wider? Is there what changes in here that makes it wider? Right, z-score, right, exactly. The z-score changes, right? So instead of a z-score 1.96 for a 95% confidence interval, for 99% confidence interval, I would use a z-score of 2.58. Why 2.58? 2.58 because if we look at the normal distribution, right, when we want to capture 99% of the possible outcomes, we're looking for 0.5% at one end of the outside of that range and 0.5% out above that range. So that would represent a value that's 2.58 standard deviations from the middle, right? So that's why we use that to represent 2.58. And we go to our table to look that up. Well, how about if I'm satisfied with a 90% certainty? Would it be narrower or wider than this range we have now? Narrower, because we can afford to have a narrower range because we're willing to accept a larger chance of being outside of that. So what area for a 90% confidence interval, what percentage of the possible outcomes would be below and above the middle 90%? What would this be? Right, for a 90% confidence interval. Right, 90%. What's going to be on both ends? 5 and 5, exactly. 5% here and 5% here, because we're accounting for the 5%, the 10% of the probabilities that we're going to get a sample outside of that range, right? If we really have this, if this is really true, that this is the true mean and that's the true standard deviation. So that's where and what's the z-score for that? That's going to be a smaller z-score because we want a smaller margin of error. That's going to be 1.64. Okay, so if we remember those three numbers, right, we're halfway home. Okay, so now let's take a look at the, let's see, let me see if there's any other questions there. Calculate standard error. Okay, now we're going to repeat this study. We're going to leave Manhattan, we're going to go to Brooklyn, and we're going to repeat this study for 16 pubs and find that a mean of 34 beers and a standard deviation of 7.1. Okay, now let's go back here and take a look at what our knowledge of this is now and how it compares to what we knew before. Okay, I'm going to get a new page. Whoops. Okay, here's our new page. And we got X bar, we've got a sample size, and we've got a standard deviation. Okay, and what was it? Sample size is equal to 16. Our standard deviation, our mean was equal to, I believe, 34. And let me see our standard deviation as well. I'm here. 7.1. So our mean is 34. And our standard deviation is equal to 7.1. Okay, now we got a small sample size, right? Instead of a big sample size, we have a small sample size now. So now we can't assume that our distribution, that we know our standard deviation well enough, or sigma well enough for the population well enough to avoid some extra uncertainty from having to guess at the standard deviation. So how do we make up for that uncertainty? We use a t-distribution that's determined by the size of the sample. The t-distribution is going to be spread out more for a smaller sample because we have more uncertainty, and it's going to be spread out less for a bigger sample because we have a bit less uncertainty. Okay, if we have a really big sample, the t-distribution is basically the same as the z-distribution. That's why we say with a sample size of 300, 200, or 300, we're not going to bother distinguishing between the two because when it's so big, that t-distribution is almost identical. Okay, so let's see how we're going to work this out. So we're looking for a 95% confidence interval now. How are we going to calculate that? Once again, it's going to be X bar plus or minus. Well, this time we're not going to use the Z distribution. We're going to use the T distribution. And that T distribution is going to be specific to the level of uncertainty we want to accept. In other words, our confidence interval. T times our standard error. Well, let's calculate our standard error. Standard error is calculated the same way, except this time it's standard deviation over the square root of the sample size is equal to 7.1 over the square root of 16, which is 4. And I'll calculate that now. I'm sorry, 1.775? Okay, great, thank you. 1.775. Okay, good. That's our standard error. So now our calculation for our confidence interval is going to be 34 plus or minus our t-value. What's our t-value going to be? Well, we can do that a couple of ways. One way is to look it up on the table. Okay, I want to get the table up too so everybody can see where it's coming from. Okay, so if I can't expand that. Okay, so how are we going to look up our t-value? Well, our degrees of freedom represent basically our sample size, right? Degrees of freedom are sample size minus 1. So for our purposes, the line we're interested in here is the line 50. First of all, number one, why is it organized this way? Why don't we have a table like we do for the Z table, where we have areas in the middle and the t-score on the outside? Why do we have it this way instead? Right? Because really, we could do it that way. The problem there is that for every sample size, we would have to have a different table, right? So we would have to have one table for 2 degrees of freedom, one for 3 degrees of freedom. We'd have to fill out a manual, a book full of tables, right? So most of the time, we're only interested in 95%, 99%, 90%. So why bother with all those other areas? Why don't, as long as you know what T is for a certain sample size, for a certain T distribution, for 90% certainty, 95% certainty, 99% certainty, that's plenty for us, right? So in fact, we actually have more. We have the 80%, we have 90%, 95, 98, 99. So, but most of the time we're going to be interested in 90, 95, or 99, and almost 90, and most of the time, just 95. So for 14 degrees of freedom, was it 14? No, we started with 15 degrees of freedom. We started with sample size of 16. What's the t-value that we want for our 95% confidence interval? It's going to be 15 is this row over here. So which row is that? That's this one right here. Now notice that it says the confidence level is 95%, but it describes the right tail probability as 2.5%. T-score for 2.5%. Take a look at that in a second. So I'm going to just get that number for now. So 90, so let's see, 15 degrees of freedom is going to be 2.13. I'm just going to round it off to that. So our t-score is going to be 2.13. Write that in there, 2.13 times our standard error, which is 1.775. Okay, now let me go back to this for a second. So let's see what does that exactly mean, that t-score is 2.13? Well, the normal distribution, the z distribution, looks something like this. And 95% of that distribution is between 1.96 standard deviations to the left of the mean and 1.96 standard deviations to the right of the mean. My t distribution has a similar shape, but it's wider. And the lower the sample size is, the wider is that distribution. So for the t distribution, 95% of the outcomes is going to be further out than for the z distribution, right? That's where the 2.13 comes in, because it's the number of standard deviations away from the middle, or the mean, the point value, that you have to be, so that 95% of the population, 95% of the outcomes or population, whatever, are between those two z-scores. Okay, well, what does that mean? That means that there's 5% left, so 2%, 0.025, on each end. So that's what it's describing there on that table. It's describing 0.025. If I can get back to it again. Let's see. I can never remember what my shortcut is for this. Let's see. I put the table away. There's the table, okay. So if I go back here and look at this, it says, 95% confidence interval. That's the same thing as a right tail probability of 0.025. Well, it's interesting they put that there, because really we're interested in a two-tailed test most of the time. But if you look at that, a right tail probability of 0.025 implies that you have the symmetrical probability on the other end, the left side. So you have 2.5% and 2.5%. That's why they put that there for the right tail probability. And it is the same thing as saying a 95% confidence interval. Okay, so that's what that table is. That's what that table's doing to us. Okay, so let's take a look at how this works out. So our 95% confidence interval here is going to be equal to, I'm going to pull up my calculator so we do it. Okay, let's see. First, I'm going to work out my margin of error. 2.13 times 1.775 equals this. And I'm going to clear out my memory first. Put that value into my memory. Clear. Okay, so 34 minus our margin of error. Did I hit the minus? Minus our margin of error. Let me clear that. 34 minus our margin of error. I killed it, didn't I? Try this again. 2.13 times 1.775. Okay, I'm going to put that into my memory. And I just said memory clear. Put that into my memory and clear the register. Okay, 34 minus, call my memory. That's going to be 30.2, and round it off for our purposes. 30.2, and the upper value is going to be 34 plus our margin of error, 37.78, or 37.8, I'll call it. Okay, there we go. So 30 to 37.8. That's quite a bit wider than our margin of error was before, right? This is only your margin of error there. Our range before was only 4. Now our range is almost 8, right? So that's quite a bit wider, and that's attributable to to using the t-value, because our standard deviation was only a little bit different, right? It wasn't twice as much. It was only about maybe, I don't know, 15% different, right? So not being able to use the Z distribution, working with a small sample reduced our certainty about where the middle of this is, right? So that's one of the reasons why big samples good, because it increases your level of certainty, okay, and reduces the range that you're going to assume that you're 95% certain. Okay, so let's take a look at another problem. Okay, let me do this again. Okay, so let's see. Before I want to take a look at a point estimate, just make sure that we understand how to calculate that, a proportion, make sure that we understand how to calculate the confidence interval for that as well. But before we do that, I just want to take these 10 numbers that are here. Secret undercover Department of Health and Mental Hygiene study of randomly selected restaurants on St. Patrick's Day. Again, this must have been a spring semester example as opposed to the autumn one that I put together on the homework. Finds that the number of slices of corned beef and lunch specials on St. Patrick's Day were as follows. I'm going to copy all of those numbers, and I'm going to open up Excel. Okay, I'm going to paste those numbers into Excel. Boom, that worked out okay. And I'm going to blow it up so we can see it a little easier. I'm going to line these up into a vertical column. Okay, there we go. 16 restaurants. These are the number of slices of corned beef that were in the sandwich in the 16 restaurants. And I'm going to say to myself, okay, let me do some calculations here. Let's see. I'm going to say, what's the average number of slices? Okay, mean is going to be equal to average, parentheses, and I'll find the average of all these. Okay, roughly about 10 slices. So what's the standard deviation? It's going to be equal to the standard deviation. By the way, you'll see me when I type in equals STDEV, and you'll find this in many of the calculations that I do. Among the suggested results that come up are standard deviation here, but there's also other kinds of standard deviation that Excel does as well. Most of the time, those are newer versions of the same function. They're functionally going to be the same, except in certain special situations. You'll see me tend to ignore that and just use the old function, okay, which is just standard deviation, because for our purposes, it's really not going to be any different. So I'm going to, that's my standard deviation. Now, what's my sample size again? Sample size is 16. I'm going to do it this way, just so we can see that you can do it. Count, parentheses. I'm just going to highlight all of these values, and it'll count it for me. Sample size is 16. So in this case, if I calculate 95% confidence interval, what am I going to use, the Z distribution or the T distribution? T, it's more small sample size. So our standard error is going to be equal to, is going to be equal to the standard deviation divided by the square root of the sample size. Yes. Okay, and that's our standard error. So what is our confidence interval going to be? Well, let's calculate our margin of error. Our margin of error is going to be equal to, what's going to be equal to? Well, I need the T value now, don't I? So let me see if I can't do that here. Equals T inverse. Let me see if this will work for me. I think it will. Okay, the probability is going to be 0.05, comma, degrees of freedom is going to be 15, right? See if I get it right. Okay, remember what we got before? 2.13, same thing from the table. So I can get that from Excel as well. Just to show you again, equals T inverse, right, parentheses. Okay, it wants the probability. Now this probability is a probability outside of that range, 0.05. 0.05. For 95% confidence interval, it's 0.05. For 99, it's 0.01, comma, degrees of freedom, which is 15. Okay, again, I get that same value. So what's my margin of error going to be? It's going to be equal to 2.13 times my standard error. Okay, there's my margin of error. So now to calculate my confidence interval, it's going to be equal to my mean minus my margin of error, and it's going to be equal to my mean plus my margin of error. Okay, so there's my 95% confidence interval. Small sample size. I did the same thing with Excel. I'm going to repeat this one more time. Anybody got an idea what I might do with it now? Another way I can solve this. I'm sure that this is a distant memory now, but it's going to come back to haunt you again. Slices. I'm going to drop it on my desktop. Nobody has an idea what I'm going to do next. How about if I start up SPSS? Let's solve the same problem using SPSS. We did it manually. We did it with Excel. Now we're going to do it with SPSS. How are you guys doing online? Okay. You guys got SPSS on those computers? Okay. Do you want me to slow down while you copy those numbers in? If you're interested in it, do it with me. I'll read them to you. If you want, I'm going to import these values into SPSS from Excel. But if you don't have them available in SPSS, what you can do is you can just go into the first column and you can type them in. I'm gonna import them right now. Open. Yes. When I did Excel.
Yeah.
You mean from Excel? Sure. Okay. I kind of ditched it, but it's okay. That's all right.
It's okay.
No, I can do it very quickly again. Now, if you have a question about it, chances are other people do too. Oops, I gotta open it. Recent slices. Okay, there are my slices. Okay, so first thing I did was calculate the average, right? I need the mean in order to calculate confidence interval. I need the standard deviation to calculate it. I need my sample size, which was 16. I know that already. I need my standard error. Well, my standard error is going to be equal to the standard deviation divided by the square root of the sample size, which is 16. Okay, so that's going to be 3 point. Did I do that right? Yeah, it's okay. Okay, so that's my standard error, right? So what is my 95% confidence interval going to be? It's going to be equal to x bar, the mean, plus or minus, right? My t value, either 1.96. I'm going to put 1.96 in here as a placeholder, but it's really going to be the t value that's based on the sample size, which turns out to be 2.13 times my standard error, which I just calculated up there. Well, t turns out to be 2.13, right? So my lower value is going to be equal to my mean, 10.025, minus 2.13 times my standard error. Okay, I think that should work, right? It's going to do the multiplication first and then subtraction. And I think that's the answer we got before. And the other way it's going to be equal to my mean plus 2.13 times my standard error. Okay, so that's my 95% confidence interval. Okay, so now I'm going to take these. I'm going to import these. Now I can open up. I can say I want to open a data file in SPSS, and I can tell it. Let's go to my desktop. Okay, I got to kind of navigate there, and I'm looking here for the slices Excel file that I just created. You might have seen me save it as slices.xl. Okay, so now where did it go? I don't see it there. The reason why I don't see it there is because SPSS right now is fixed to only open file types of SAV, its own file types. So if I click on that and change to Excel files, you will now see that file. And there's the file I'm interested in. I just created it before I saved it after I copied those numbers in. So I'm going to say, let's open that. SPSS brings up a window which tells me, first of all, do you want SPSS to read a variable name from the first row of data? Well, you guys may remember there was no variable name at the top. It didn't say slices, just had a data number. If I don't uncheck that, it'll think that top number is the name of that variable. So I got to uncheck that. Okay, and it says it sees data from A1 to A16. So that tells me it's really keyed in on the data I want. I'll click OK, and it'll open up a new data file for me with those numbers. So I'm going to read them quickly if you want to type them in. 10. Now you could actually, if you just wanted to do it this way, you could literally just type in these values: 10, 7, 14.0, 13, 9, 7, 12, 15, 10, 12, 12, 8, 9, 6, 4, and 13. Okay. Apparently nobody put half a slice into the sandwiches. Right? The discrete values because nobody used half a slice. All right. So, since I didn't give it a variable name, SPSS automatically assigned it when it calls it V1. If I wanted to go into the variable view, I could recode that column, that variable. And I can say, oh, that's slices. That variable name is slices. Whoops. Okay, remember the rules. You got to start with a letter. You can only have letters and numbers. Okay, can't have any spaces or special characters. And I'm going to give it a label. Okay, I'm going to say slices of, what did I say, pastrami or corned beef, right? Slices of corned beef. And all the rest of this, it's not a nominal variable. It's guessing it's a nominal variable because it sees only integers. It really isn't a nominal variable. It's a scalar or numerical variable. Okay, so I need to change that so SPSS handles it correctly. Okay, so I've changed that. I'm going to go back to the data view, and you'll see that it changed to slices, right? The variable name. Okay, so now I'm going to do my calculation. I'm going to go up to Analyze. I'm going to go to Descriptive Statistics, and I'm going to go past frequencies. Frequencies is usually used for nominal variables. You're going to do counts, right? You're going to count the number of left-handers and number of right-handers. I'm going to count the number of people in this age range, this age range, this age range. I'm going to count the number of redheads, brunettes, blondes, so on and so forth. So I'm going to go instead to either descriptives or explore. I'm going to start with descriptives. I'll click on descriptives. You could use either one of them. And now it asks me what variable do you want to move into the workbox. Okay, well, I made up two other variables inadvertently because I was typing in numbers to show you how to do it. So I'm not going to ignore that. I'm only going to move in the variable slices. Okay, now I have a number of options. If I open this up, it says, oh, it's going to calculate the mean, the standard deviation. I'm going to add in the variance, the range, just for the hell of it. I'll click continue. Notice I don't see confidence interval in there. I'm going to click continue, and I'm going to click OK. And it's going to go ahead and do the calculation for me. When it does the calculation, it opens a completely new window called an output window where all of the output information is stored. So what did it find? Well, the sample size is 16. We knew that. The mean was 10.062, the same thing we calculated by hand and by using Excel. And the standard deviation was 3.12. I don't see the confidence interval here, right? So we need to go a little bit further. I'm going to go back up to Analyze again. Anytime we want an operation done, we're going to go to Analyze. Analyze Descriptive Statistics. I'm going to go past frequencies, descriptives. I'm going to go to Explore. Explore is going to give us descriptive statistics again, except it's going to give us more different kinds of statistics, descriptive statistics. and it's going to give us the opportunity to do some other things as well. So I'm going to move slices into the dependence list, right? And then I'm going to go into statistics, and it says, oh, well, look, descriptives, confidence interval for the mean 95%. Not only do I have the opportunity now to have it calculate the 95% confidence interval for me, but if I want to change that, I could calculate the 99% or the 90%. Or if I really wanted to be freaky, the 87.5% confidence interval, right? Literally anything we wanted to put in there. It can do some other things like calculate percentiles for you and so on and so forth. For right now, that's what we're really after, the confidence interval. It's automatically going to calculate many other statistics, but for now, it's going to do it automatically for us. So I'll click continue. I'm not interested in any plots right now, but if we wanted to, we could ask it to make some additional plots. It's automatically going to do a box plot for us, no matter what we say. So right down here it says, what do we want it to display? Just the statistics, just the plots, or both? I'm going to leave it on both and say OK. Again, it does a calculation. It creates an output table, and here we are. Okay, so what do we have here? Well, the sample size is 16. The mean is, as we said before, 10.063. It's got the median, the variance, a whole bunch of other stuff. Well, notice now it calculated the standard error for us as well. So having the sample size, the mean, the standard error, now it can calculate for us the confidence interval as well. Okay, so did it use the t-score or did it use the z-score? It used t. How do we know that? We know that because it came up with the same answer that we did when we used 2.13 instead of 1.96. Okay, if I have a sample size of 300, is SPSS going to use the t-score or the z-score? It's going to use a t-score. If I have a sample size of 5,000, what's it going to use? T. It may use it no matter what the sample size is, it's going to calculate a t-score, and it's going to use a t-score, even if the t-score is 1.9600000001. It's always going to use a t-score, right? Because it has that facility. It's not. It doesn't have the constraints on time or accuracy that we have. Right? So it's always going to use a t-table because that's the more accurate one, and also because it's reflecting reality. We never know what the population is. No matter how big the sample is, we never really know the population mean or standard deviation for sure. Okay, so just to go back, I'm going to do one more thing with confidence interval, and then we'll move on to some problems that involve this idea of hypothesis testing. Okay, and the last thing I want to do here is I want to do something with proportions. Okay, so but we're going to work, it works exactly the same way, except that, don't we have some rules about proportions? Wasn't there some kind of rule about proportion that we had, that they had to have a certain sample size, right? Not only that, but wasn't there also a rule that you couldn't have a situation where you had like 100, where you're talking about if you had a proportion where you had 100 people and say the prevalence of something was 20%, you had 20 people and you had 80 people in the two groups, so it was 20 people and 80 people, so it was 20% of the people had the disease, let's say, the prevalence was 20%, 20 out of the whole 100. But if you had a situation where you had 4 out of 100, right, the fact that the sample size was 100, you still had the problem that that was too small a group. Even though the sample size overall was large enough, you really needed the sample size at both ends, yes and no, to be sufficiently large. When they're sufficiently large enough, we generally fall back on the z-score. We don't play around with the t-score. Okay, we're going to work with the z-score here. Okay, simply because we're justifying it by the fact that one of our assumptions is our sample size is always going to be big enough to justify using the z-score for our estimate, okay, of the confidence interval. Okay, so I'm going to look up one of these problems, and let me see if I can't get it back. I lost that Word document, so I'll reopen it. Yeah, go ahead. Okay, so let's take a look at this. Okay, I'm just going to do the first part here. Oops, Come on, scroll. Okay, suppose we want to know the true population proportion of Irish Americans who approve of a wider representation of groups. This was a big deal back when I first made this problem. If you remember the issue of gay, gay groups marching in the parade. I think they march in the parade now, don't they? Right? Do they have gay groups in the St. Pat? Am I wrong about this? Right? They do now, right? They still keep them out, or they do now? They do now, yeah. Okay, suppose we want to know the true proportion of Irish Americans who approve of a wider representation of all groups in the St. Patrick's Day Parade. In 2000, the parade committee asked for a random sample of Irish American parade participants if they approved of wider representation. Out of 1,381 respondents, 496 said that they approved. Okay, so let me get a fresh piece of paper here. A fresh piece of imaginary paper, I mean. Okay. Okay, so let me work on this. Okay, what do we got here? So we had, how many did we say we had? We had a sample size of 1,381. And how many approved? 496. So what is our point value here? It's not the mean, right? It's the proportion, right? And instead of calling it P, what did we do when we were talking about the mean? We took X, put a bar over the top of it. That indicated to us it was a sample mean. So to indicate that this is a sample proportion, not the population proportion, I'm going to put a cap over the top of that. See the cap? That means sample proportion. So what is that proportion? Anybody calculate it yet? 0.36? You're invited to all of my classes from now on. Okay, any class you want to show up for, just turn up. Okay, 0.36. Okay, so now we know a sample size. We know our sample size justifies using this idea of the z-score instead of going to a t-table, right? Big sample size, sufficiently large, yes and no, for a proportion, or successes and failures for a proportion. Okay, so now what do I need to know besides that proportion? I know I'm going to use 1.96 for our z distribution for a 95% confidence interval. Okay, what else do I need to know? I need to know my standard error so I can calculate my margin of error, right? So how do I calculate my standard error for a proportion? It's equal to the square root of, anybody remember? Times 1 minus p. Right, all of that under the square root sign. That's all they're going to work that out first and then find the square root. Now, sometimes some equations you'll see p times q. Q is just another representative for way of representing 1 minus p. So don't get fooled by that. So that's going to be equal to the square root of 0.36 times 0.64, right? That adds up to 1 over the sample size is quite large. 1381. Okay, so let's do that calculation here. See, now I'm rushing because I want to get it done ahead of you. 0.36. Now you got my competitor's uses going. 0.64 divided by 1381 equals. Okay, that's the inside of that square root. Right? Now, it looks like a very small number, but because the square root is a number that number is the square. The square root is what the number which, when multiplied by itself, will give you that number. So the square root is actually, in the case of a fraction, larger than the square, right? So when I take the square root of this, it's going to become a bigger number. Okay, so now it's actually 0.0129. I'm going to call that 0.013, 1.3% basically, right? 0.013 is 1.3%. So I'm going to call that 1.3%, 0.013, right? So my standard error is equal to 0.013. So what is my 95% confidence interval for the true proportion P? Well, it's going to be equal to 0.36, right? Plus or minus 1.96 times 0.013. So that's going to get even bigger now too. My margin of error now is going to be 0.36 plus or minus 1.96 times that number. As a matter of fact, I still got it there, so I can say times 1.96 equals 0.025. 0.025. That's my margin of error. Those two numbers multiplied together. So my 95% confidence interval is going to be 0.335, right? To 0.335 to add 2.5% to that, 0.385. Right? In other words, 33.5% to we're 95% certain the true proportion of Irish March, of all the Irish marchers, is going to be between 33.5% and 38%. So what does that suggest to you? That suggests to you that at that stage in 2000, not today, we're 16 years later, a lot of things changed in the last 16 years, right? At that stage, 16 years ago, less than 50% of that population didn't approve of opening the parade to other groups, right? So that tells us something about this. It's a tool for us. Okay, so we use the idea of margin of error, standard deviation. Very similar here, standard error, very similar in proportions as we did to, we use them in a, when we're talking about when the point estimate is a mean instead of a proportion. The main difference was the way we calculated the standard error and some of the assumptions that we had to make. Okay, but otherwise we handle them pretty much the same way. Okay, so now let's take a look at this idea of using this idea of confidence and the Z table and the T table, using this kind of another way. So I'm going to open up the other document. I'm going to say, okay, let me see what time it is, where I want to start here. Okay, so now I'm going to say to myself, I'm going to apply this a somewhat different way, okay? And I'm going to take a look at this. The mean SAT score for the population of first-year students at Hunter is 620. That's the mean for all first-year students. The standard deviation of scores in this population is known to be 95. So I know their mean and I know their standard deviation. An investigator believes the mean SAT score for first-year psych majors is different than the mean of psych scores for the entire population. It's different than the entire population. The mean of this, he takes a sample of 36 first-year psych students and finds that the mean of their SAT scores is 648. Okay, so let me see. Let's write down what we know here. Okay. So what do we know here? We know that for all students, right, the mean mu, right, because we know what it is for all students, is 620, and sigma is 95. Okay, and let's see. But now we're interested in how this compares to psych students. Well, psych students, we didn't have the time to sample all the psych students. So we were only able to get a sample of 36. And the mean there was 648. X bar is equal to 648, right? And the sample size was 36. I'm going to say to myself, I have no reason to believe that the standard deviation for the psych students is any different than it is for all students. So I'm going to use the same standard deviation, maybe a little bit of a reach, but I'm going to use the same standard deviation and say I know the standard deviation of this population. So now I want to see if I can apply this to say whether or not there is a difference between these two populations. Okay, so the way I'm going to do this is first, I'm going to set up a couple of hypotheses, right? I'm going to set up a null hypothesis, and I'm going to set up an alternative hypothesis. Okay, So my null hypothesis is, what do you think our null hypothesis is about the means of the total population and the mean of the psych majors? They're the same. Okay, I'll write that this way. Remember, I'm talking about the mean of the population. Mu of all equals mu psych, right? What's the alternative? What's the alternative to that? It should be an A there. Mu of all does not equal mu of the psych students. Okay, so now let's set about testing that. And one of the ways I might be able to test this is to see how far apart these two values are in terms of standard deviations, right? Remember, where a 95% confidence interval was based on this idea that if we were within two standard deviations either way, that we would catch 95% of the possible outcomes. So I'm going to put that to work right now, and I'm going to say to myself that the z value, the difference for these two, I'm using z because I'm saying I think I know the population standard deviation. The number of standard deviations between these two groups is going to be, it's going to be equal to, let's see, it's going to be equal to the difference between x bar and the mean of all. X bar for the psych students, which is all I know, and the mean that I know for the population. This is a known value, right? This is just a sample value, right? This is what we call a single sample t-test. I've simplified it here by saying that we know the population standard deviation, so we can use the z-score, right? But we normally call this a one sample t-test. Why is it? Because I'm only taking one sample and I'm comparing it to a known value for mean, right? Or something that I speculate I know well enough to call my known value, right? So it's the difference between the mean for my sample versus the mean for all students divided by, what do you think I'll divide it by if I'm interested in the number of standard deviations? I'm going to divide it by the standard deviation, sigma, right? Just like we did before with our various populations and so on. Okay, so now, I'm sorry, excuse me. Yeah, good work. It's standard error, right? Why is it standard error? Because we can't forget that the sample size is going to have an impact on this. We're comparing our mean of our sample to all the possible means we could have got instead. So really, we don't want to use the standard deviation. We want to use the standard error. And what's the standard error going to be equal to? It's going to be equal to sigma over the square root of the sample size, which was 36, right? So what is that equal to? It's equal to 95 over 6. And what's that? Oops, I lost it. I don't know what happened to I lost my, what's that? 15.83. I'm going to call it 15.8 for our purposes for now. So that's equal to 15.8. So what's our z-score equal to? It's equal to x bar, which is 648, minus, what does it mean for the population? 620, right? Over 15.8. And since I lost my calculator, I'm dependent on you guys to tell me what that is. What was that? 1.77. That's our z-score. So what are we saying here? We're saying that these two values, that if I were to draw this distribution of all the samples that I might get, for given that my mean is 648, my sample size is 36, I'm assuming our standard deviation is 95, then how often would I expect to get a value as far away as 620? Well, it's only 1.77 standard deviations away. So is that more the tail end there? In other words, the values, the percentage of the time I would expect to get a value that small, is it less than 2.5%? What I would expect if I wanted 95% certainty or 5% chance of being wrong? Well, no, it's not. It's not greater than 1.96. If it's not greater than 1.96, it's not far enough away from the known mean, or the two values are not far enough apart from each other to be able to say that I have only a 5% chance or less of that being the actual same value for the two populations, that occurring if I took samples of that size from the real population, right? So do we get the idea here? What I'm, I'm perhaps not as explaining this as clearly as I would want to. I'll think about it. I'll think about another way to do it, maybe on one of the homework examples or something like that when I do a review. But in order for me to say that I'm 95% sure, less than 5% chance that I would be wrong, and if I said this, in order to be able to say that, the two values would have to be two standard deviations apart, or greater than 1.96 standard deviations apart. Okay? So since it's only 1.77 standard deviations apart, can I go back here and say with 95% certainty that, I don't remember where I put it. Oops, where did I write that? Did I write that on here? Right here, it's my null hypothesis. Can I say with 95% certainty that I can reject the idea that they might be from the same population, right? I can't, because I need for the z-score to be bigger than 1.96. So what do I say now? I can't say I reject the null hypothesis and accept the alternative hypothesis. What can I say about this now? Anybody want to hazard a guess? Can I say that, oh, I've just proven that the mean for psych majors is equal to the mean for everybody? Have I proven that? No, I haven't. What I really wanted to do was be able to reject this and accept the fact that they're different, with a small chance of being wrong, right? So I can't say that this is true. All I can say is I failed to reject the null hypothesis. In order for me to reject the null hypothesis, I have to have less than 5% chance of being wrong. And in order to have that small a chance of being wrong, these two values have to be 1.96 or more standard deviations apart. Okay. Now let me ask you something. If this sample size had been 16 instead of 36, how many standard deviations apart do you think they would have to be then? Would it be 1.96 again? It'd be the t-score. What was the t-score? We just did it for 1.96. 2.13. They'd have to be 2.13 standard deviations apart for us to be 95% sure that they're different. In other words, less than 5% chance of being wrong if we reject the null hypothesis. Okay, that's how now we're starting to shift away from this idea of confidence interval and start to apply the same ideas to the idea of comparing two groups. In this case, we're not really comparing two groups yet, right? We're comparing a sample result to a known value, one sample t-test. Okay, so I'm going to open SPSS for a moment, and I'm going to go back to the example we just had. Okay, and what if I told you that in Boston, we know that the average number of slices that are in corned beef sandwiches on average in every Irish pub in Boston is 11 slices. And I asked you to tell me, let's set up we have a sample in New York. We know it's 11 in Boston. We have a sample size of 16 in New York. And we want to test the hypothesis that there's a difference between the two of them. So let's set up our null hypothesis. Okay, so our null hypothesis is, okay, here we go. So in Boston, we know mu for Boston is equal to 11 slices. Okay, in New York, we know X bar. We have a sample that we just collected in New York, and the sample size is equal to 16. I haven't evaluated it yet. All I know is the sample size is 16. This is a known value. This is from a sample. We're going to have X bar. We're going to have a standard deviation from this sample. The sample size is small, so we're going to use the standard deviation of the sample, but that's going to mean we're going to have to do a t-test, right? Not a z-test. Okay, so I'm going to look at this. Let me set up my null and alternative hypothesis. Well, first of all, what's my null hypothesis? The mean number of slices in New York is equal to the mean number of slices in Boston. What's my alternative hypothesis? They're different. New York does not equal Boston. Did I make a judgment yet that one is more than the other? Just that they're different. So it doesn't matter whether my t-test comes out with a negative number or a positive number for a t-score, right? So let me ask you something. If I were to calculate this now and get a t-score, right, for the difference between when I compare my sample mean and standard deviation, when I work this all out and compare it to the known value of 11 slices, what does my I want to have less than 5% chance of being wrong. I want to have less than a 5% chance of making a type 1 error, rejecting my null hypothesis when I shouldn't be, saying he's guilty when he's not guilty, right? Saying when he's innocent, right? So I can call that a type 1 error, but I'm going to call it an alpha error for our purposes from now on. I want my alpha error, my type 1 error, to be less than 0.05. What does my t-score for a sample size of 16 have to be greater than in order to be able to say that? It has to be greater than, what did we say? 2.13, right? If the sample size were 300, what would it have to be greater than? Have to be greater than roughly 1.97, right? Pretty close to 1.96. If our sample size were 4, what would it have to be greater than? Well, I could go to the t table and look up what value of t represents 3 degrees of freedom for 95% confidence, right? So I can use that table for this purpose as well. When I use it that way, I'm saying that I have a value of t that I have to exceed to be sure that I have less than 5% chance of being wrong. I'm going to give that a name, that value of t. I'm going to call that the critical value. So if I exceed the critical, if my t-score is bigger than that critical value, I'm going to reject the null hypothesis. Okay, well, I'm going to do this the easy way. I'm going to go to Excel, to SPSS, also because we're late. I'm going to SPSS. I'm going to go take a look at my sample again, and I'm going to go up here to Analyze. Now, we could do it by hand, again, just like we did before, calculate the mean, calculate standard deviation, the standard error, the margin of error, calculate the difference between the two. I'm sorry, not margin of error, but calculate the difference between the two. I'm going to go up here to compare means, right? So I'm going to compare means. I have a couple of things here. One of them is means. One's independent samples t-test. How come this looks like this? What happened to my? Let me try opening the output page here. Window. Okay, analyze. Compare means. Compare means. I'm having a reason why I'm having a problem here. Let me try something here. Okay, I'll do this again. So I get an output page. Here we go. There's a bug in my version of SPSS. The tests don't all show up unless I have the output window open, right? Kind of cool, right? Interesting bug. So did you notice how all of a sudden now I'm doing the same thing and like many more tests show up? I'm going to go to Analyze. If yours does the same thing, which I hope it won't, if yours does the same thing, open an output window and then do the same thing you were going to do, which is go to Analyze, go to Compare Means. What kind of t-test is this I'm doing now? Is it 2 independent samples, a sample in Boston, sample in New York? No, it wasn't, right? New York, Boston, we knew. We knew that the value was 11 because we sampled everybody in Boston. We took the average of everybody. So if we had sampled 16 restaurants in New York, 16 in Boston, that would be independent samples, right? But we're doing a one sample t-test. We sample New York and we're comparing it to a known value in Boston. That's a one sample t-test. So right now it's asking me, okay, what's a test variable? Well, it's slices of corned beef in New York. And what are you going to compare it to? I'm going to compare it to the value 11, which is the number of slices that we know to be the true mean for Boston. Okay, I'm going to click OK. Let's see what we get when I complete that. Okay, let's take a look here. And if I look down here, I'm going to do this again so that I can scroll up. Okay, there we go. There's the table at the top here. What's my t-score? Minus 1.98, right? And what is my degrees of freedom? 15. And okay, so what would you say if that's our t-score? What's our critical value? What do we need to exceed for a t-score? Right, 2.13, right? Did we exceed it? No, so we failed to reject the null hypothesis. I'm going to do it again. Analyze, descriptive statistics, crosstabs, compare means, single sample t-test. And this time I'm going to say, oh, they're really generous in Boston. They put 14 slices on their sandwiches. I know that that's a true mean in Boston. I'm going to run this test again. Okay, this time, what did I get this time? This time I got a t-score of 5. Can I reject my null hypothesis now? Am I bigger than my critical value for this sample size? Yes, I am, right? I'm bigger than 2.13. It does, well, what it's saying is that it's comparing our value 10 to Boston's mean of 14, right? So you're subtracting 14 from 11, x minus mu, right? That's what you're doing. Comes out a negative number. It really doesn't matter if it's less than left side or the right side. Works the same way, right? That's what we're calling a two-sided test. Remember, we didn't make any kind of judgment about whether it's smaller, if Boston has fewer slices or more slices. We just said different. Our criteria was that the two means were equal or the two means were different. Without any concern initially whether which one was greater than the other. I'm going to make this a little bit smaller because I want to show you something interesting here also. I'm going to call this 12. See if this will work for me. Okay, what does the t-score come out this time? 2.4. Can I reject my null hypothesis? Yes, because with that big a t-score, I know that there's less than 5% chance I'm wrong if I reject the null hypothesis. One more, I just want to show one more thing before I take in. Well, look at this over here, significance two-tailed. That is the real probability of being wrong if you reject the null hypothesis. Anytime your t-score gets big enough, you're going to see that significance, that p-value, becomes smaller than 0.05. They go together, right? That's the real value. When we're working with a table and working by hand, we don't get a chance to calculate that p-value, right? Because we don't have like a z-table, built into our heads like SPSS does. But SPSS actually calculates the t-score and the probability of being wrong if you reject the null hypothesis, calculates both. So you have a little bit of an advantage. I'm sorry, what was your question?
Answered it.
What's that?
You answered it. I was going to ask you if that's the p-value.
Oh, okay, yeah, that's the p-value. Same thing as the p-value. The probability of being wrong if you reject the null hypothesis. And in order to reject the null hypothesis, we want our chances of being wrong to be less than 5%. Okay, guys, so I think we got to call it a night. Okay. I see people yawning, so I know. Okay. You think that, well, okay. Okay. Hopefully, as we go on and we work with some more real world examples instead of this kind of like bogus, really known kind of stuff, and maybe we find some real data, we can make this a little bit more interesting. But now we have a tool. We went from this idea of a confidence interval to an idea where we now, if you can imagine, we have a way of comparing two groups, Boston, New York, America, France, beef eaters, vegetarians, and so on and so forth. We have ways of comparing groups. And next week, we're going to get into comparing independent samples, where you can actually do studies where you split people up into two groups, take samples, and so on and so forth, and do some really interesting stuff. Okay, so good night, guys. How about you guys online? You okay?